Oh, no, got it. So welcome everyone. I have to start with an apology. My original plan was to dive deep into this paper before I would present it and really understand all aspects of the mathematical theory, the proof, and then present a numerical implementation with some results. But I just got back from travel and I just didn't have time to spend a lot of time on this. So I apologize for that. You can leave at any time if you, of course, that's always possible. But and if there are any questions, let me know. So this paper, so in the last few years, I spent a lot of my time, I guess, more on statistics, mathematical oriented problems journals. And so I work with colleagues, as we all do. And one colleague, he's really good at sending papers. Have you seen this? Have you seen this? Have you seen this? And this was one of these papers that my colleague Case shared with me, I think about half a year ago or so. And because we've been talking about machine learning and that deep learning, these I still call them neural networks or artificial neural networks, that they yield phenomenal results, but they're very difficult to interpret. And so we've been thinking about alternatives for several years already. And then he said, yeah, there is a lot of literature on kernel machines, and that was very popular with a lot of theory, but people don't use that very much anymore because it's all deep learning, neural networks. So, and then he shared his paper, which I thought was very interesting because the author of this paper, Pedro Domingos, shows with the mathematical proof, which, by the way, if you go online, people have issues with some of that proof, but in general, the idea holds that if you have a deep learning model, a neural network, that you can approximate that with a kernel machine. And a kernel machine is much easier to interpret. Think about, I don't know if all of you know what a kernel is, but think about nearest neighbor interpolation. So let's say you have a map at a fixed elevation, you have temperature. Let's say the Earth's surface, you have temperature based on measurements. And now you like to predict what the temperature is at a location where you don't have an observed temperature. You can do that in different ways. Geostatistics is the way to go with a variogram, creaking, all that stuff. But one other method, a simpler method, is nearest neighbors, where if you predict at a certain spot, you just look at the data points closest to that spot, and the weight you assign to each surrounding sample where you have an observed temperature is based on their distance. So the closer the data point is to your location where you want to predict what the temperature is, the higher the weight becomes. And that's essentially a kernel. The relationship between the distance and the weight distance, that's a kernel. And so you can think of a neural network where you have many more variables than temperature, right, as some high dimensional kernel. And so if we would know that kernel, then you can see the relationships between the variables and how they relate to distance, etc. So it's much easier to interpret. It's also easier to train. So let's go to this paper. So there is kernel machine. This is the general formulation. Y is some variable. G is a nonlinearity, what they call. And so here we have a summation where K is your kernel. So suppose I have X and I have Xi. So I have training data points Xi. This is some function, and this is my kernel that tells you that if I have training samples and I have a new X, so these are my measured temperatures, say, and this is the or the locations of those. This is the location of the where I don't have a measured temperature. Then based on some kernel and an intercept, and then I can add a nonlinearity on top, I predict what the temperature is at that location. So here is our kernel. So it's a summation over all your samples. But there are different formulations. I personally don't like this formulation very much. I don't think it's particularly intuitive. So the idea here is that the author of this paper, Dominguez, shows with the proof that if you do deep learning and you follow, in this case, the weights, how they change as function of time, that's a trajectory in weight space, that in that trajectory is all the information to derive that kernel. And so to get to that theory, we need to define a few things, one of which is a loss function, L, which is just the summation over all your samples of an individual loss for each sample, and then you sum over all the samples, you get your joint or total loss. And W0, those are your initial weights. So let's forget about the biases in the network. Let's just focus on the weights. We can add those biases to the weight factor, but let's simplify notation. So W0 are your initial weights. Now, gradient descent step. So W, I don't like the notation. I often have an issue with that. Some journals are different. I personally would write W as lowercase upright bold to indicate it's a vector. So W here is a vector, okay? Suppose we have D weights, where D is, can be on the order of thousands. So this is a vertical vector, D by 1. Then this is a vertical vector, D by 1. Then this is a scalar, which is called the learning rate between 0 and 1. You don't want it to be 0, because then there's no learning takes place. But the closer you get to 1, the closer you are to gradient descent, right? You use a standard step length. The Nepla operator indicates we're going to take derivatives of the loss function with respect to each individual weight. So this thing returns what we call the gradient vector, which is D by 1. It's the same size as our weight vector. Now, and this is a scalar, so a scalar times a vector that is D by 1 creates a D by 1 vector, and if you subtract that from your current weights, you get your new weights. So this is the standard gradient descent recipe. You determine at your current location the gradient derivative with respect to each parameter, and then you take a step, and that should lead to an improvement. Certainly if your step is small, but if you make your step large, then you may overshoot and actually deteriorate. Now, then there's a definition here that relates the gradients at S and S minus 1 or S and S plus 1 to that kernel. So essentially, the author says that if you integrate all those gradients step by step, that you arrive at that kernel. So you can essentially, if you do neural network training, and you, instead of returning only the predictions of the network, you would, at your final weights, you would return all those derivatives, that entire path where you're learning, you return those derivatives, then in those derivatives is the information to obtain that kernel. And then essentially you're done. Now, so here is a two-dimensional example where we have our initial weight. So assume we only have two weights, W1, W2, and W0, those are the initial values. The 1 and the 2, I shouldn't have used that, that's confusing, but W0 is just some weight here, some weight on this axis. So we only have two weights. And then this apparently is the trajectory, hypothetical, and here we arrive at our final weights. And here we go from, in the first step, this is our first update. With the given learning rate, we arrive here, and then we arrive here, and then finally we arrive here, and then we arrive here. So at W1, we can determine the gradients of the network with respect to both weights, right? So here's the output of the network, and these are, as far as I understand, training samples or so. I think when I go with you, I'll show a numerical implementation. I think it's more intuitive. So when I first looked at this, I thought that this was simply the resulting, in a force field. You have one force, you have another force. I thought, oh, this is the net force essentially. But if you look here, that doesn't seem to hold up unless it has to do with the projection or so. Anyway, I'll get back to that. Definitions, theorem, and now a proof. Okay, and most steps of the proof, all steps are actually, I think, quite understandable. Again, I didn't have a lot of time to look at this. I apologize for that. I did implement, and I'll show you a MATLAB example where the kernel comes out of those gradients indeed. So here, this is the Newtonian formulation of a derivative, as far as if I remember things correctly. So new weights minus the old weights, if you divide that by a small scalar, you get an estimate of your local derivative. Okay, so the issue is always, what do we choose for epsilon? And so there are procedures online in MATLAB, Python, where that choose that epsilon value so that your numerical derivative gets as close as possible to an analytic derivative if it existed. That has to do with Romberg extrapolation, Richardson's extrapolation. Those are standard techniques from the 50s and the 60s, published that Romberg is in a Norwegian journal or so, as far as I remember, that talk about numerical derivatives. Now, so loss function, so you can essentially write this approximation as dwt dt. I don't like this notation. The differential operator should be upright, not italic, because now it looks that this is a product of d and t, or that dt is a single variable. Okay, this is a common mistake. This should be upright. In LaTeX, mat remove. I think mat remove it is. Then it's upright, or text instead of regular mathematical variables. Okay, so apparently this formulation is known as gradient flow because this is the gradient. Okay. Now we're going to apply mathematics for any differentiable function. So this is important. The function itself, the loss function, needs to have certain properties. Okay. Continuity, that you can take derivatives at every single place in the space, the loss function space. So if we take derivatives, this equation actually doesn't have much to do with this equation, but this is just known formulation dy dt, summation over our d weights. Remember, we had a vector of weights, d weights, and you can write it as this product. So this and this cancel. So essentially, you write this derivative as a summation over the individual derivatives. Now we can do a substitution because you see this and you see this. So now what you can do is you can replace this term with this term. But here you see a j, whereas here it's over all the weights, because this is the gradient. This is an n by, or the d by 1 vector. And here we're talking about a scalar. So what the author did, instead of using the Nepla operator here, which holds for all the weights, he now switches to the differential, the partial operator here, where you now only take the derivative with respect to wj, because that's what you need to do. So this essentially is the same equation, except with the notation changed for this last term. Now, this equation, you can write it as this equation. That's the so-called chain rule, right? Now we have a summation, and we have a summation here. So this doesn't change, this term, and this term we can write as a summation as follows, where this is over the samples. We have M samples, training samples, and we have D weights. So we have D unknowns and we have M training samples. So then once we have this formulation, you can rearrange. So based on this is why the properties of the loss function are important, because if the loss function doesn't satisfy continuity, etc., then this doesn't hold up. Okay. So regularity conditions, under usual regularity conditions, so if you have a standard loss function with certain behavior mathematically, then this will hold. Okay, so now we arrived here, and now essentially we're going to replace these terms with some of what the author has defined before, that this term here, this first term, is simply the loss derivative with respect to the output, no longer the input, the weights, okay, that's important. This is the output. And this was defined as a kernel that was defined in up here, definition 1, or here. I think it's, let's see, it's somewhere defined here. And so there's a substitution takes place. So up to here, that's easy to follow. Then you substitute. And now we still need, the question is, okay, this trajectory, does this depend my kernel on the initial model, my initialization of the weights, yes or no? So if you define y0 to be your initial model, the y values, the output of the network at your initial weights, then this is a differential equation. You can move the dt to the right-hand side, right? And that means you have dy on the left-hand side left. If you integrate dy on the left-hand side, you get y. So that's what you have now. And you have a y0 as an integration constant, right? So now we have y is y0. We have that right term. We take an integral dt. So now we still need to solve for this integral, right? So where ct is your entire trajectory over the weight. So that is this figure here. That's this trajectory. So now you apply mathematics and you can rewrite this equation, or you can write this equation as this equation, and based on definition 2, ultimately you arrive here that your y is a summation over all your training samples of ai, a kernel, plus b. Personally, I would have written the b in front, because when I look at this equation, it may be confusing. Is this b in the summation operator, yes or no? So to avoid that confusion, but this is just an intercept, essentially. It's a bias, not a bias in the network, but essentially it's a vertical shift. So that is the proof. So when I saw it, and then there are no examples in this paper, okay? Only discussion. So this apparently is a big result. So when I saw this, I was like, okay, I don't really understand the details, and question here, question there. Talked to a few colleagues. So this was months ago. And then after our last information theory meeting, someone reminded me, oh, Jasper, you're next. And so I thought, oh yeah, I'm next. Okay, let's work on it now a little bit. So I opened MATLAB and I took the paper, and if the mathematics is easy enough, then I don't need numerical examples to see what's going on. But when it gets more difficult, I usually always try to code what's in the paper to really understand, because that understanding is in details. And dimensionality, vectors, matrices, how does it all work? So that's what I try to do. So I asked ChatGPT, hey, write me a code. Here, this paper, I pointed at a paper to this paper. I said, hey, can you write me a code that implements what's in that paper? Now, within 30 seconds, I think this is what ChatGPT 4, before ChatGPT 5 was out. I don't know, I forgot. But it came up with a recipe, but that didn't work. It's just a starting point. So for those that procrastinate, right, that's a really good thing, ChatGPT, because you have something to start with. So let me go over the example that I created. So 50 training data points. I should have called this M instead of N, because in the paper it's called M, but I'm always used to using N for sample size. Anyway, we have 50 training data points. Then I only have 2 dimensions. I keep it easy. I first want to understand, how does this work if my network only has 2 weights? So here I assign the values of the weights. Weight 1 is 2, weight 2 is a half. Then I create what's called a design matrix. I draw random samples between 0 and 1. Okay, uniform, standard uniform distribution. So I get a matrix of size n by d, which is 50 by 2. So x is 50 by 2. Now I have my data generating process where linear algebra, I just multiply n by d matrix with a vector that is 2 by 1. So I get 50 by 2 times 2 by 1. Inner dimensions match. End result is 50 by 1. So this is a vector of 50 by 1, which is W1 times X1 plus W2 times X2. Then I define a measurement error, small error on my training samples. And here are my final data points, which is the data generating process Y plus an error, which is just standard normal with a variance of 0.01. Then I create what ChatGPT called query samples, evaluation samples. So I have 1, 2, 3 samples at which I want to evaluate my network, which in this case is going to be linear regression, and at which I want to evaluate my kernel as a comparison. So here I ask, how many training samples do I have? M. Learning rate, I set it to 0.5. I started, we can set it smaller, no big deal. Between 0 and 1. And number of training steps. So now what we're going to do first is we're going to use the training samples with gradient descent to determine W1 and W2. And they should come out to about these values because they were used to create the data Y. So here is gradient descent implemented. So here I define the initial weights, which I set them to 0, but you can set them in any other value. And I define that I don't have an intercept because I only want 2 parameters to understand how this works. So the weights, it's easiest. Here, I store the gradient information. Remember, the kernel is based on the gradient information over that entire trajectory. Now, the gradient will be a vector of 2 by 1 because we have 2 parameters, W1, W2. So that's going to be 2 by 1. Then I have n samples. So I need to do that for n samples. And then I have t training steps, so a maximum of 100 steps. And what I do here, I see that I did add, to make it all work, I did add a 3rd dimension to my gradient vector, but that's constant. That's the value for the intercept, so it's going to be 0. Here I store the values of the weights during training. So at each t, I get a W1 and a W2. So this is going to be a vector of 2 by 100 in this case. And here's the value of b, which this is not interesting. This is just going to be 0. Here's gradient descent, forward pass, and then the gradients. So my prediction is my design matrix times my current weights. And the current weights are going to be 0 in the initial step. So at my first training step, my predictions are going to be 0, 50 by 1, a vector of 50 by 1, because I have 50 training samples, right? So 50 values of y. So this is going to be 0. Then I calculate the residual, and now I determine the gradient with respect to w, the weights, and the gradient with respect to the intercept. But that's 0, but it's just there. This is math. You can derive this analytically, that this is how you have to do it. So once you have your residual, 1 divided by the number of training samples, that's 1 divided by 50 times x transpose. Now, x transpose, x is an n by d matrix, right? So this becomes d by n, and this is a residual factor, which is n by 1. So d by n times n by 1 is going to be a d by 1 vector. So the gradient with respect to 1 is indeed 2 by 1, because I have 2 weights. Okay. Gradient with respect to b, the sum of the residuals is a scalar. This is a scalar, so this is going to be a scalar. Yeah. Now, we store the current values of w in our history. We store the current value of b in our history. And now, based on the gradients, I can derive the individual gradients. I can derive the gradient with respect to the function, weights and bias. So the prediction, output. Remember, if we go back to the paper, we replace that's this here, this thing here. This is the loss function with respect to the output, no longer with respect to the parameters. Okay, so we have the gradient with respect to the parameters here. This is the gradient of the output. Now, here it is. And then I can calculate the new weights. I implement that first equation here, this equation. Here, this equation, that's essentially here. New values of the weights are the old values plus the learning rate times the gradient. And then the new values of b. And now you wonder, why is there a plus here? Because there is a minus here. Now that's the way you define your residual. And this is one of these things that took me years to understand. And finally, many, many years ago, I stumbled on it. There are many mistakes in papers about this, that if you define your residual to be your predicted value minus your measured value, then this may be a negative. Whereas if you define this to be your measured minus predicted, and that's what it should be. If you look in the literature, what is a residual? Residual is always measured minus simulated or predicted or fitted, not the other way around. So if you do it consistently, you either do gradient ascent or gradient descent. Anyway, it's all consistent. So here the residual is defined as y measured minus predicted. And this is a vector, right? N by 1. So in this paper, there should be a plus if you define the residual correctly. I mean, what I call correctly. Now we have all these gradients, all this stored in the history. So now my idea was, okay, can I now put this into practice, this theory that's visualized here, and this, can I now put all this together? Because I have my trajectory, I have 100 steps. I have my trajectory, that is the history, W history. And then I have these derivatives. So if I now integrate this, is this working anyway? So that's what I'm doing here. Approximate that kernel. So I implement 2 different methods, a fast method and a slow method. Okay, so you see that in the fast method, we only loop, we have a double for loop. Whereas in the slow method, we have a triple for loop. This may be, that's always with coding. That's why I usually implement different methods, because when you work on something, you finally, you work on it, you're really in the material, then you understand the fast method. But then a year later, you go back to your code, you look at it again, you're like, what the heck is going on this line, right? And so that's why it's always useful in my view, to document the slower methods as well, because it's easier to read. Fast codes, in my experience, are usually not easy to read. So here, we take the gradients at a given, for a given sample, and at a given training, and you do this inner product. Important here, this is a dot product. Dot product. Okay, what is a dot product? We also call that a vector inner product that results in a scalar. So if you have a horizontal vector times a vertical vector, and they both have the same number of elements, that gives a scalar. So that's a dot product. So this results in a scalar. So if you look at this, then this was, let me see here. So this is a vertical vector, right? And then we make it horizontal. And this is vertical again. So this is horizontal, because this by itself is vertical. We transpose that. So this is d by 1 or d plus 1 by 1. It's d by 1. D plus 1 by 1. We transpose it. So now it's 1 by d plus 1. And we multiply it with a d by 1 vector. So that's a vector in a product. So this is a scalar. And you add that to your current values. That's the integration. When you go for all the samples over time, you keep adding that. Now, anyway, this gives a kernel. I multiply that kernel with the learning rate. And this was one of the questions I had. Now, the methods, I can run the code, you'll see it all adds up. Once I have my kernel, I can evaluate this kernel at my new points, and that gives a prediction. And I'll show you that both create, I think I ran it before, so here's an example. So this is training sample, this is the query samples, evaluation points. Remember, I had 3 evaluation points. Here they are. This is the first, this is the second, this is the third. This is actually out of sample, because my inputs are only between 0 and 1, and I'm going out of sample. It's actually interesting to see what happens. So here's the result. So this is the true result. Then this is what my gradient descent result is using my final weights. So this is the true data generating process. This is what my gradient descent gave when I used the training samples, because they have a small error, they're not identical. And you see that my kernel is identical to my gradient descent. So this simple example shows that if I take the gradients of the parameters and then the gradients with respect to the network output, and I store all that information, I then use that to compute the kernel the way it's defined as here in the paper. I then use that kernel that I actually match the gradient descent results. And this is only a very simple example, but at least I was happy to see this, that this is indeed equivalent. And obviously the question now is, there's one thing I noticed quickly, this kernel becomes very high dimensional. Let me run the thing here. Get some new results probably. So here are new results. Oh, the training hasn't been, oh, let me, I need to do more training. When I slow down the learning, I need to do more steps. So let's do 1,000. It should be better now. Yeah, it's getting there. So if you now look at the kernel itself, so the size of that kernel, it's 50 by 50. So I have 50 training samples. It's 50 by 50. So if we have 1,000 training samples, 10,000, these kernels, they grow very rapidly with dimensionality, number of training samples and number of parameters. So that's a huge limitation, obviously. Anyway, this was the main thing I wanted to have shared with you. There's still a few things in here that I took 2 hours, got it to work, but I still have to look at much better. But the initial result is very promising, because if we can indeed do this, that means that any machine learning model that we end up with in hydrology, that in principle, we can summarize that with the kernel. And going back to the paper, there's one interesting thing I want to show. And that is here, this figure here. Then the way to think about these deep learning models, that in essence, that your prediction is some weighted combination of all your training samples. That's essentially the point of this, that any prediction of a deep learning model is just a weighted combination of your training samples. Going back to that example I gave with temperature, when you predict, you just take by the nearby samples, and that's essentially how it works. So if we can figure out what that function is, that kernel, and how that behaves with other variables, so in a multidimensional space, then we have a much better understanding of what's going on, right? So that's the general idea, is deep learning, essentially the answer is just a weighted combination of all your training samples. And that's much easier to interpret, because it's like nearest neighbors, where you can look at that relationship between distance and weight, where that's not the weight in the network, but it's the same, yeah. So that's essentially what this paper is about. I did briefly spend time on people that criticized the mathematics, but the general conclusion, some disagreed with, but overall I felt there's consensus that that's about right. And then one more thing, a colleague of mine also said, Jasper, you need to look at the neural tangent kernel. And the author of the paper also refers to this several times, the neural tangent kernel. And he said 2 days ago when we talked about it, he said, you should look at the Wikipedia, because it has a nice summary that gets the main idea. And so I think we talked about this in a different context before, but essentially, as far as I understand, is that this shows that when you make your input layer infinitely large, that the training of the weights actually, how to formulate this? So you would think each node you add has a weight and a bias. If you take depending on the transfer function you use, but as a weight and a bias. So each additional node you use adds parameters. So the neural tangent kernel essentially shows that if you make that input layer infinitely large, that the training, let's see, it's summarized here, but that the training itself, the parameters, you would think you have so many parameters that training becomes really difficult. Actually, training becomes easier. The changes you need to make to the weights become infinitely small. If you have enough, nodes in the first layer, and that was the point of this paper that's based on mathematics, but this is a very, maybe you all know about it, but it's something to look into. And it's shown here essentially that if you make the network, the way I see this, more and more complex, you train more and more. At one point, you go perfectly through the data point. So this is highly over-parameterized, and that the training actually becomes easier. You end up in local minima, no doubt, right? but that the changes you need to make to the weights become infinitely small because you have so many weights that you can produce the end result in so many different ways. So I need to read this better. And because it's true, that's infinitely small, you can use a Taylor expansion. Because if the weight changes required are so small, the Taylor expansion works really well. Based on the local gradient, you get your final estimates immediately because you're in that window of really small change. Anyway, so this is, and then richless versus rich regression, that's just adding a regularization constant, okay? By the way, there's a mistake here. This is not correct. This should be X transpose X. This is the Kranian, but this is wrong. The T should be here. Because now this is a design matrix N by D times N by D. So it should be X transpose X and then the inverse thereof.
And also X transpose before the Y. Yeah.
So I was surprised that that standard least square, where this is your covariance matrix or an estimate, you miss your sigma square. But anyway, so I'm sorry I couldn't do more than this. I spent a little bit more time, then I could explain to you in detail every single step, including also how we compose this. But you see this in the MATLAB code. And yeah, that's usually how I learn. I see something and I implement it, and then I try to understand what's going on. But I honestly just didn't have the time. I hope this was sufficient for now. So if there are any questions, otherwise I can show you something else later. And that's a paper that Allison actually presented earlier. I saw that on YouTube. And I did that earlier in the summer. I wrote an implementation of this paper by Peter-Jan van Leeuwen, where I verified all his results to understand how these M-links work. So anyway, that's a toolbox I just wrote to understand more about information theory, etc. But for now, it's this stuff. So if there are any questions or any ideas or something, let me know.
Any ideas on how this generalizes to stochastic gradient descent?
Talks about that in the paper.
That's written in the paper here. So let's see.
Remark 5, yeah.
And this is a little bit of hand waving, but basically Dominguez Pedro writes that it's no difference. Your samples, I assume, need to have a certain size. Can imagine some robustness, but other than that. Oh shit, did that answer your question, Joseph?
Yeah, that's good, thanks.
It's a little bit of hand waving. This remark by Hoshin, I saw you have you raise your hand.
So question. If I understood this correctly, saying that the prediction is made as some interpolation from the training data, and it chooses which training data, so which neighbors, where the neighbors are defined in some fairly complicated way, which has to do with the gradients rather than actual positions. Yeah, because if I remember right, he says something about the similarity in the gradient space, but and so you're basically saying that depending on where you want, which prediction you want to make, where it is in the target space, you choose a different set of samples and some weights, and those are combined together to make the prediction. Did I understand that correctly?
I would phrase it slightly different, but yes.
Where the set of weights is determined by the kernel, right? Yeah. Yeah, okay. So one of the things that it seems to me that we try to do, when you talk about memorizing the data, that effectively says you store everything, right? which, and you can store it in a compressed form, and that's fine. So you only store the non-redundant parts of the data. And then you have some rule for decompressing and then choosing which components of that you want, and then you make your prediction, if I understood all this correctly. Okay. But it also seems to me that one of the reasons that we build models is to not have to store all of the data. In other words, we want to store some kind of compressed representation. I'm just curious if you thought about that in the context of this, because this almost suggests that what the deep learning algorithm is doing is just storing a compressed representation of the data in the sense of non-redundancy, and then using a kernel approximation to reconstruct the prediction, which, and then I'm more interested in the problem of how you generalize from that. So are there any implications of the stuff that he talks about in the paper here?
No, that's a really good question. I actually thought exactly about this question during the flight yesterday. That what you ideally want scientifically is that your model does not require all the training samples. You would want that to be compressed in some physical law. That's the highest level of compression, I guess. Newton's law or something else. So I think because that takes a lot of memory if you have to store all the training samples.
Mm-hmm.
My idea was reading this paper, and I have to look at it again, and then I can answer your question better. But my idea was that the kernel essentially, that is the compression that shows the relationships, and that your evaluation points just act on that kernel. So in our case, this kernel, these are the kernel values with 50 training samples. And it's a symmetric matrix, so you can throw half of the matrix away. But that my idea was that all that information is summarized in this kernel. But you see the kernel, this will grow rapidly. If we have 1 million training samples, this is 1 million by 1 million. So then we need to have better storage. But this is obviously not desirable. So when I ran into this, the first thing I thought, oh, what is the practical applicability? Because this may sound nice, but in practice, this becomes very difficult to work with.
So,
but yeah, your point is well taken, is that ideally we don't have to store any of the training samples, and all that information is in the kernel, where we only enter a new position, new data point, and then with the kernel that tells us what the prediction should be.
So building on that, surrogate vector machines are also kernel machines, right?
Yes.
And my understanding is that the kernel is kind of like an infinite dimensional object in principle, but is represented symbolically as a much lower dimensional object, right? So that sort of sounds like what you're talking here. As you process more and more data, you replace the data with a kernel, which is effectively infinite dimensional, but is actually represented in some lower dimensional regularized representation as some kind of basis functions.
Yeah, no, your points are spot on, Hoshin, as usual. So, so this obviously, I didn't realize this limitation as much, but when I saw this example and how quickly that kernel gets so large, but in essence, I think the underlying idea that a deep learning model, essentially that every prediction you do is some weighted combination of all the existing training samples, I think that fundamentally is a really important idea, that that it's not some black box, but there's actually, that's the way the network ultimately works, that it is a way that as in nearest neighbor, essentially. But then in a high dimension, the question though is like, when you really look at the kernel methods, why are they not used as much as, or why is that research abandoned? The problem is high dimensionality. How do those kernels look in high dimensions? In lower dimensions, it's a lot of literature, but in higher dimensions, it's very difficult. The relationship between distance and if you look at the spatial interpolation problem, distance and then Gaussian, that's the standard kernels, but the kernel may not be Gaussian, and how to do that in high dimensions and how to train. So yeah, I thought it was interesting because it's something different than what people are doing. I think it warrants looking deeper into this because it helps a lot with interpretation. What's going on here. And that's what I miss with a lot of the machine learning literature. It's so focused on prediction. I can do better with this metric or this metric, but what are we really learning from it? But that goes back to why this group started, this information theory, essentially. We try to extract relevant information from the data instead of just data fitting. Yeah.
The other thing that came to mind, oh, sorry, go ahead, Joe.
Oh, I was just gonna ask, so is the kernel or the K matrix a matrix only because this example is 2D then? So turn into a tensor once we go beyond 2D?
This indeed, when you go to 3, 4, 5 dimensions, it becomes an array of 4, 5, 6 dimensions. Yeah. So
Okay.
so that is becomes a high dimensional an array with dimensions here. So let's see, where do we compute it? So we have I and j. So yeah, it is ij and then by the number of parameters minus 1 or something. So yeah.
Sina?
Yeah, thanks. So I got a little bit confused here. Is that, I mean, I got the point, but when you calculate like the non-parametric kernel, like K here, the K matrix, is that, but in the query phase, you're not using this, then you have to like calculate it all over again.
Yeah, so that's good for a good thing. So you use the gradient, you use the storage here. So gradient of the network output that is used here. So the trajectory, sorry, where is it here? The trajectory is used. But the that's a good question, yeah. So I can look into it further, but yeah, so at this point, this K value actually, now look at it, it's not directly used. It uses this component in prediction. Oh. And then the gradient at the query is the X, and then the ones for the intercept, which we don't use, but because the derivative with respect to the intercept is 1, dy db is 1.
Yeah. And like just like what was the M dimension here?
M is the number of evaluation samples.
Oh, M is the number of evaluation. So in the query phase, we don't really need. So I was thinking like the matrix of the kernel will not be as big as the matrix that you just showed. It will be only the dimension of the points. We still need all the sample points to calculate the gradients. I mean, the gradients should have been saved somewhere, but
yeah, so it's better if I rewrite this and I use the K that is computed here, because this makes no sense. So give me, I need to find some time, but yeah, you can write the prediction as function of the kernel you compute here. And so, because we're doing it over again here with the whole trajectory, but we should use the original kernel instead of recomputing the kernel based on the query point. But in essence, this kernel, to answer your question, about the size or the data points and all that. Its size is number of data points by number of data points times the number of parameters you have. So this blows up, and that's a really huge limitation. So what I expect that we use this kernel, we add the evaluation query data points, and that's how we get to our prediction. Because there's another step here. I compute multiply with the learning rate. To me doesn't make sense, and then also here, but that is that makes it work. But why that is? So that's why I said I wish I had a little bit more time. But I hope my goal was to point you all to this paper and the general idea that instead of using deep learning, that there are alternatives. I'm not saying that they're easy to implement numerically. It is maybe, but mathematically in higher dimensions, there's still theory needed on how to exactly do this. But I found the idea that in essence, what the network learns is the weighted combination of the three. I find that very inspiring.
Yeah.
Thanks, Jasper. What occurs to me is that so there's the universal approximation theorem, which actually goes back to Kolmogorov. There are many modern reproved versions of that for different kinds of basis functions. There's the Kolmogorov-Arnold theorem, which also shows how you can construct a model as a combination of basis functions. There's the paper which proves that any deep neural network is effectively a decision tree. I don't know if you guys have run across that one. And then you have this paper, which basically says any deep neural network can be effectively thought of as a kernel machine. And what that makes me think of is that these are just, not just, but these are multiple different ways, different perspectives on the same learning problem, kind of like the blind man and the elephant. Each of them gives you a different kind of insight into the nature of the learning problem or the representation problem. And we end up using the one presumably that's easiest to implement. And so in this case, this is showing a theoretical result, which is interesting because it helps us understand a different perspective on what's going on, but it may not be the method that you would actually choose to implement it. And then at the end of the paper, he points out that to use this as kind of like a thought basis for developing new research directions, for finding different ways to explore the parameter space or the learning space or so on. I mean, the thing that comes to mind to me is that if you think of the prediction problem as being choosing which data points and the rule for how to interpolate them, the kernel, in some sense, that's not terribly different from a large language model or transformer network, which says that given where I am in the data space, this is the interpolation rule that I use to predict the next word. It's sort of like a context-dependent kernel machine.
Yeah.
Yeah.
Yeah. So, yeah, I mean, I'm very much attracted by theory, and I was communicating with Gray the past few days, and he's now in Zurich, in Switzerland, and so I was talking about some of the work that we're doing, and I wasn't surprised by his email or anything, but I guess that there are quite a few people that think that when it comes to deep learning, all this type of stuff, that that the main theoretical questions have been solved essentially. That it, we can use PyTorch and build a deep learning model of a lot of things, and there are all kind of issues still, but it's more or less an engineering problem then. And I fundamentally disagree with him because
I think Gödel put an end to that conversation, but anyway.
But because the things that we talk about are so simple, for instance, about loss functions. A lot of loss functions have been defined, right? All kind of variants, and you can add an additional term, an additional term, an additional term. You can train whatever you want. But from a statistical perspective, that affects convergence rates. If you give that stuff to statisticians, they look at that and say, okay, but what is it that I'm estimating here? What is the convergence rate, right? What are the consistency? What are the asymptotic properties? All these things that turn out to be important if you really want to know what you're doing. That is just one area where, yeah, there's so much work to do for theoreticians. It's easy to come up with a new loss function, right? To just add another term and you can train a network, whatever you want. There's so many questions already related to that.
If
Anyway,
I can build,
yeah.
if I can build off that, Jasper, I think it's the paper by Wilson, where he points out that essentially the biggest problem is how do we define similarity in a very high dimensional space?
Yes.
Right.
Yeah.
And so kernels are a way of defining similarity, but you have to learn what that similarity metric is. And you have to learn it in very high dimensional space. And in the Wilson paper, he basically points out that that's what deep learning models do. They figure out how to learn a similarity metric in a very high dimensional space, which is very hard for us to imagine necessarily, especially when you have high dimensions and that space is not full of data, right?
No, you're right. You're right. Yeah, that's so in my view, there's still a lot of work to do, because that's so beautiful about a lot of the theory that it gives you guiding principles that you know if you satisfy certain assumptions that you know what you're actually estimating. And I think that's also required if you want to have robustness when you're confronted with data you've never seen, that if you can rely on certain theory, then at least that constrains the space of possible outcomes, what you can expect. But I fear, I mean, we talked about this before. Things are going so quickly that it's hard to make people enthusiastic sometimes about theory. Yeah, but it is what it is. So by the way, one thing I saw that Allison was also there, but one thing that opened what I never realized related to this paper, Allison, and I didn't know that you presented this paper, Allison. So this summer I wanted to know more about information theory. So I dove into this paper and I decided this was on my desk already for 2 years. And so I thought, okay, so I coded the whole thing, spent quite some time on it. I've now, all the results are now generalized and I get the same results, but I never realized that with information theory, that you need a lot of data, meaning that if you look at the Lorentz, just the Lorentz equations, right? This is with 3 state variables, X, Y, and Z. And then you look at mutual information and you look at how that evolves in time. If you want to estimate mutual information, conditional mutual information, joint mutual information, if you want to estimate those really accurately, you need a lot of samples. And that blows with the number of dimensions. So this paper uses 50,000 samples. That's only 3 variables. But if you add the 4th, the 5th, the 6th, so that's another thing I never realized. Maybe most of you knew that, but that indeed, that's a limitation with information theory. I mean, Jose, you published a paper about it. How do you measure entropy, right, from discrete data?
I'm not sure I completely agree that it's a limitation of information theory. What I would say is that it points out that there is no way to learn without regularization. So any quantity you want to calculate If you say, I'm just going to calculate it from the data, it's just not possible. You have to give a rule for calculating it from the data, and that rule tells you how to regularize the data. In other words, you add information that's not in the data, or that is hard to extract from the data. So if you want to calculate mutual information using smaller numbers of samples, you just have to regularize the rule for calculating mutual information. But then you run into the problem, there's how much of the information came from the data and how much of it came from the rule. But that's fundamental to learning, right?
Yeah.
If I give you two data points, x1, y1 and x2, y2, and I say, here's what I know, and now I give you a new value x, and I say, what's the value of y? Okay, there's no way you can tell me what that answer is. You have to postulate a linear relationship or a
Yeah.
relationship or something, right? So people like, especially frequentists, like to say, oh, we just want to know what the data tells us. We don't want to impose anything on top. To which my response is, that's not possible. At the very least, you have to bin the data. You have to do something, right? And any
Yeah.
operation you do,
Prior, in essence, some prior.
any operation you do to get information means you have to interpret the data in context. So you have to throw the data at something and see what sticks, essentially.
Yeah. And as long as you can have an asymptotic proof that when sample size goes large, that you results are independent of your prior or whatever assumption you made. But that's so Hoshin, maybe other, for instance, in this paper, which is van Leeuwen, truncates each variable. So we get X values, Y values, Z values of, this Lorentz system at each time. And then you do 50,000 time values. So now you have 50,000 by 3 matrix. And what he does, he looks at each individual variable, makes a histogram, and then transforms that to a truncated Gaussian. So he throws out 4.25% on the left, on the right, and now what you get is a distribution. I hope you can see it, that it looks like this, right? Before, and then afterwards there's a peak here, and then it goes up like this, and there's another peak here at the lower. So I played with this because I didn't really see this. I read some of Profane's papers, maybe. Anyway, I tested this with or without, has no effect. But I thought maybe this is something you do when you have small samples or so, that you have problems at the edges or so, where you have data and then you don't have a sample or whatever, that you can't, like if you compute what is it, the Kullback-Leibler divergence or so, and likelihood, and you don't have a sample. Anyway, point is, I don't know if this is familiar to people in this group, that you actually do this before you calculate any of these information metrics, that you actually truncate the data.
Well, you may truncate the data. Sorry, Joe, just one more comment. But in principle, when we talked about information bottleneck papers, one of the critiques that was leveled against the people who wrote the paper was that there's no, it's hard to calculate mutual information, for example, or entropy or whatever accurately, because you end up having to do some kind of thing. So if I give you a data set, I can make the entropy calculation give me an answer which is logged to the number of data points, because I put a bin on every single data point, or I can bin it, aggregate and so on. And I can get, so part of the problem of using entropy metrics like that is you have to first agree on some smoothing rule, right? And your proofs, even the proof in this paper, is assuming smoothness and continuity of some kind. So we end up having to do that. Whenever we do that, that's regularization. So if you have discontinuity, then you have to know where the discontinuity is, how to represent it. And you always end up having to deal with this problem. Yeah. Sorry, Joe, go ahead. Yeah.
Yeah, I just wanted to say that I've had the same issue with these information theory things. Like whenever I try to implement or calculate information theory, I can never make the values make sense to me. Like it's always seems to be inaccurate. But to resolve that, there's actually a proof already in the feature importance literature that the universal predictive power, if you assume cross entropy loss, is exactly equivalent to mutual information.
Yeah.
And yeah, I recently added that proof to the hydrology literature in a preprint. And yeah, that formulation always works way, way better for me than trying to mess with the mutual information packages.
The alternative way, which I'm deeply interested in, is you use description length. So you convert everything to bits, but then you have to decide to what level of precision you're going to work. So it doesn't matter what you do, you end up having you end up having to make some kind of regularizing assumption.
It's not necessarily true though. I mean, I just stick whatever I have in random forests basically and make it predict, and that's basically.
No, I'm saying if
mean,
you want to use information theoretic metrics, the
yeah.
one I've been interested in is the one where you basically use everything as bits. Yeah.
Okay.
In other
Yeah,
words,
so I
everything
think
has
it's
been
nice.
a discrete number of bits. Yeah.
Sorry, Ocean. Yeah, if people are interested in this code, I'm trying to translate it to Python and I'll put it online. I think it's interesting. Alison again presented the paper. This mlink stuff is interesting, but there are actually quite a few statements. I know Paitian that I didn't expect. That are, I think, incorrect in that paper that he makes about. At least I think they're incorrect. Quite fundamental statements, but people are interested. This works with any data set. Again, you need a lot of data if you want to go through these higher order links. And I was just trying to understand how this relates to the work Profane has been doing, and etc. When they talk about synergistic information, etc., total information, is this all the same concept? Alison probably knows the answer to this. I don't. So.
I think Alison's gone. Yeah.
Yeah, she waved. Yeah. Anyone else?
I just wanted to clarify to Joseph. So basically, if you say that your uncertainty is represented by a certain number of bits, a certain amount of bits of information that you would have to give me in order to reduce my uncertainty to 0, then mutual information would tell me how many bits of uncertainty have been reduced by me giving you that new piece of information. In other words, that's the amount of information that was shared between the two variables. So it's just a different way of looking at it. Rather than looking at it in continuous space, you look at it in discrete bit space.
Ocean, can I ask you one question?
Sure.
It's about something else, but something I briefly wanted to show you. So so for a while I was working on this M estimation, not really, and then I noticed that stuff is not being used in hydrology. So, and then I thought, is there a way that we can make, is there a way that we can make some of these metrics more robust? So if you look at Ness Sutcliffe, I went to ChatGPT, and ChatGPT immediately suggested a robust alternative to the Ness Sutcliffe efficiency.
Okay.
And here, so this is the infamous Ness Sutcliffe efficiency. And so here is the alternative where, anyway, this is a different topic, but what I wanted to know, is this of any interest? Because now you replace the Ness Sutcliffe has in the numerator has the sum of squared residuals.
Mm-hmm.
And that's not robust against outliers and all that, to outliers. So you can replace that. That's the idea of M estimation. that you replace that. Here's a figure, I think. The
Have you talked,
standardized residue.
have you talked to Richard Vogel?
I have not specifically about this, but I was going to write him because
He is deeply interested in this subject of robust estimators, and I think he calls them L estimators. I'm not sure exactly what his term for
yeah,
them.
yeah. L
Um,
moment, yeah. But it's
yeah.
it's related to yeah.
And how you calculate things, and by making them insensitive to outliers, and which is what you mean by robust estimation. Um, so to my knowledge, in our community, he's the one who has thought about this the most.
Okay. But do you think it's of interest? Because essentially what you want, and that's why I usually do an R square, an NSE, or a KG by itself doesn't really say a lot. Robustness is that if you give different data sets for training, that you consistently get the same parameter estimates.
Correct.
That's robustness. So that is convergence in your parameter space.
Correct.
Obviously, if the system is non-stationary, there are all kind of issues.
Well, in
And
your model
it's
space
easy,
more generally. Yeah.
it's easy to show that when you use these robust estimators, that is more true, that the parameters tend to converge better to stable values.
And I think Tim is very interested in that subject too. Yeah.
Yeah. And I agree completely. But if that's the goal, right, you can design an R squared using MAT or Huber loss, or, as we've discussed, you can project all your data into a Gaussian space and then compute your metrics there. And but yeah, the question is that what people want? Because Nash-Sutcliffe is often justified in subjective terms, like we're doing this because we put extra, emphasis on matching the high flows, and that leads to more, higher variance in your parameters. But I think in another sense, it might be also compensating for your very skewed data distribution. But what's correct? Yeah, that's depends on what you're trying to do. As you guys have, you've beaten me over the head with that point many times.
I have
So
a Go ahead, Jasper.
yeah, so in your KG formulation, or the formulation for KG,
Yep.
the M estimation suggests to replace the mean, the A and the B, I think you call them, to replace those with the mean, replace that with the median.
Correct. So
And so that, because that's a more robust location estimator, the median.
yes, but here's my more general point, and it's exactly the problem I've been working on recently. The problem with reducing everything to a single loss value is that fundamentally it can't be robust. Okay, because you're trying to estimate parameters in some high dimensional space by reducing the loss down to a single dimensional space. And by definition, there are going to be an infinite number of points in that parameter space that gives you exactly the same loss value. Yeah. Okay. So when we worked on when we proposed the multi-criteria approach, the whole point was to say that if you have 10 things that you're trying to estimate, you need 10 criteria. I mean, this is, when you do linear, you know what I mean? They have to be, you have to have a full basis. You have to span the full space, the information space. And so you need 10 equations to estimate 10 unknowns, right? 10 equalities to estimate 10 unknowns, right? So to me, part of what makes KGE interesting is that we said that instead of reducing it to a single number, you reduce it to a set of 3 numbers, okay? The mean ratio, the variance ratio, and the correlation, right? And what is the correlation? The correlation is cross correlation is really the same as the mean squared error if you have subtracted out the mean and divided by the standard deviation. Okay. So if you take your data and you subtract out the mean and you divide by the standard deviation and you calculate mean squared error, you get exactly the correlation coefficient, the cross correlation coefficient. Okay, and that's in the derivation of kg. So what is the function of the mean and the standard deviation? They're just descriptors of the data. Okay, they're properties of the observed data and properties of the synthetic data, sorry, the model data that we want to match up. Okay. If I say, here's an object in three-dimensional space, and I want to create a model of it, I would have to give you a set of descriptors of this thing, and your model would then match that set of descriptors in order for you to say, oh yeah, that looks exactly like this phone. Okay? You wouldn't reduce it to a single number. You would never reduce it to a single number. Okay? So what information theory tells me is that here's an infinite dimensional object. I want to model it with a finite set of descriptors. Okay? And then I have to be very precise about those descriptors, and I can only match this object up to those descriptors. Anything which is not in those descriptors, I'm going to ignore. So that's how I make a model of something. I take a real car and I take a model car, and my model car is only equivalent to the real car up to a set of descriptors. Yeah. And I claim that these are the only important descriptors and I ignore everything else. Yeah. So fundamentally, my view is that yes, robustness is interesting from a statistical viewpoint, but there's a different kind of robustness which has to do with the fact that you have to actually come up with a way of compressing your data down to a set of descriptors. And then your model, you have to compress down to the same set of descriptors, and then you have to make sure that every one of those descriptors matches up. And so then it becomes a vector. So you can put those descriptors into a vector in some dimensional space. And then you can put the observed vector and you can put the modeled vector, and then you want to make those vectors match.
Yeah, so I think that the deeper underlying question goes back to how to do inference with a misspecified model. And essentially, what you're saying that when we rely on the assumption of a correctly specified model, everything goes back to least squares or so, or weighted least squares. If we have heteroscedastic errors, or if we have correlation in the errors, we can do generalized least squares, because that all follows from theory. But once your model is misspecified, your description of the phone, your model of a phone or a car is actually knowingly incorrect, then using such a loss function implies a loss of information. Any loss function implies a loss of information. So the idea is which moments, generalized moments estimation is an example of that. Which moments do we want to match? Which features that you call? So that's why
That's absolutely correct, Jasper. Another way to think of it is that your real object lives in a particular dimensional space and is represented by a vector of properties. And your model lives in a lower dimensional space, is represented by a vector of properties. And the challenge is how do you make the distance between the vector in the lower dimensional space and the vector in the higher dimensional space as small as possible? Yeah.
Yeah, so we got this paper now. I can now present it as another time, the A and the B. I remember last time I went to the dentist. Oh my God, I was high when I got back. I don't know what was in that. Anyway, so yeah, so the central question that keeps me awake for many years is, can we build theory on that? Under misspecification, what do you do? And there may not be one answer. But that essentially, it's good that you reminded me, Hoshin, about because in a 2024 paper, I criticized the R squared for not being elicitable. It's not an elicitable functional. Essentially, when you calibrate, and I call it an R squared, because in my view, that's a semantic discussion, NSE or R squared. And R squared cannot become negative because the value you use in an R-square is supposed to be the fitted value. And that's supposed to be good, whereas an NSE can become negative because you're allowed to put any value in there. Yeah, you raise your hand, so.
Oh, no, I'm just following up on what you're saying. The other person who has looked at this problem is Doherty. And if you look up his paper about null space projections, remember groundwater, that's exactly about this problem. Yeah. And then there's another guy in atmospheric science. I think he's now in Colorado. And he gave a talk here at the U of A, and he was basically, again, pointing out that, when you build a model, you build a state space, but your model state space is smaller than the data state space. The data lives in a higher dimensional state space than the model. And so the mathematical question, the theory question, is how do you do that projection in such a way that you don't lose something that's important? Yeah.
Yeah, so the whole clue debate, in hindsight, the whole clue idea, and I talked to Keith about it, and he talks about Shannon entropy actually in his 92 paper, is essentially that you want to temper learning. That's what you want to do. That's what clue is trying to do, that you get data under correct specification. There's so much amount of information in that data according to Fisher information or observed information, whereas we know, because our model is misspecified and other things, that information, we should temper learning so that we end up with a larger uncertainty. So in my view, if that paper had more been written from an information theoretic perspective, we would be having a very different, in some sense, different conversation today, I think. So that's why this information theory group is so good, because we're talking about units that, in my view, are, what do you call that, lowest level, highest level, but in terms of information theory, that is the most abstract concept, essentially, that makes it really good, but also difficult, because A and B may contain a lot of information. A may contain a lot of information about B, but information theory doesn't tell you how we go from A to B. That's the one. So, but that is another discussion. Yeah.
That's partly why I have been firmly convinced onto the side of thinking about everything in terms of bits and discrete information as a discrete entity. Because a lot of the complications when you try to work in continuous space don't exist when you work in the discrete space. I'm not saying that it's wrong to work in continuous spaces, but I think it creates a lot of mathematical complications, which are sort of unnecessary to the foundation.
Yeah, that's,
trying to do. Yeah. And the reality is we can only ever store information as bits. I mean, and work with it as bits. So my view is, why fight that?
But what if you need to compute the gradient?
Yeah, but you can still only compute it to a certain degree of precision.
But can you take with these discrete estimators, do they have, gradient functions that you can plug into stochastic gradient descent?
Oh, don't misunderstand me. You can still use symbols which mean things. Okay. But the symbols are by their very nature discrete. So we can imagine a continuous space, and we can imagine using discrete notation language something that exists in some latent space that is continuous. And we can figure out how to do that with theory and all of this stuff. But when it finally comes down to doing computation, you end up having to do it back down in some discrete space, which necessarily involves truncating the representation to some finite precision. As long as we stay in the theoretical space, we can work symbols and we can talk about pi and sine and cosine and so on. But when you put it back on a computer, that's the point I was trying to make.
Jasper, can you remind me, you mentioned your 2024 paper, and I liked the how you described or used the term elicitable. But can you remind me, I thought you had said that there were that some, I guess, conventional metrics are elicitable, like the RMSE, because of the or the mean being, anyway, sorry. You had
That's
mentioned that
okay.
there were a few conventional metrics that were elicitable. Which ones were
Yeah.
they?
So the mean, the median, and quantiles, those are elicitable.
Yeah.
So elicitability is a difficult concept, but the way I think about it is that if I hit someone, I elicit a response from that other person. The person may start hitting me. So by my actions, I do something that results in a response. And so a loss function works that same way. When we define a loss function, we elicit a response from the model, meaning the parameters are going to be trained in such a way to satisfy, minimize, maximize that loss function. And if we want the model to get the mean of the distribution right, then we can define a loss function that will minimize or that will get the mean right. We can do the same with the median. Because then if you take the sum of absolute residuals, then you'll get the median right. An L1 loss function. L2, you'll get the mean right. If the model is perfect, that's why we get the bias variance trade-off, because the model is not perfect. Meaning, now, quantiles. If you want to say, I want to get 2.5% or 97.5%, we can define a quantile loss function. Those are the only three properties that are elicitable. Any other thing is not elicitable. But this is in a forecasting perspective, when the data come in. If we do training, like what Hoshin with the KG, that's why I like that much more. The way I look at it from a decision theoretic perspective, in the KGE, you make explicit what you want your model to do in some way. You say, I want the mean, standard deviation, and I want my correlation coefficient. I want that to be, so you make your essentially very explicit and clear about the training. And the point I've tried to make in that earlier paper, and a lot of work we do, what we often do in hydrology, a lot of applied science, we take a loss function and then we evaluate the model for something completely different. That's not fair. If you want to use a model to do task A, then you need to train the model on task A. And then you can really compare models with each other. How good are they at task A? So that's that concept of elicitability. And what I have a problem with the R square, essentially the R square, you're telling your model, I want you to describe the entire hydrograph to perfection. That's what you're telling when you use an R squared. And we know that the model is not able to do that. We know the model can't do that. So that's why it's not elicit. It's an unachievable call. You're asking the model to do something that you already know is impossible.
So Stephen isn't here, but I think because I was reading his 2010 papers kind of at the same time, looking at your model evaluation paper, your 2024 paper, and it seems to me that Stephen's argument was that like trying to separate those two. So so training models on information to maximize the information that you extract from the input data, and that is separate from evaluation. So that sounds different from what you're saying, that you need to train on the same with the same objective, so that
Yes.
so that your training reflects the purpose. Whereas I think, and I maybe you guys know or understand his work better than I do, and please jump in, but I thought that his point was that you train with the objective of maximizing the information that's extracted from the input data, and then you apply your values, or your loss function should be, after the fact. Does that ring a bell, or does that?
Yeah, rings a bell. Hoshin,
know?
yeah. Hoshin, go ahead.
So a couple of things. One is if you take KGE to its logical conclusion, you get KL divergence. Okay. KL divergence basically says I'm going to match every single quantile. Okay. Anyway, enough said about that. I think the distinction need to make, Dan, is related to information bottleneck. So you can take the input data and you can compress it down and extract all the information that's in the input data, right? And you can do that without regard to what you're trying to predict, right? That's the first step of the information bottleneck. The second step of the information bottleneck is it says, now I've learned a representation. Now I want to throw away or keep only the part of the input data that is useful for predicting the output. Yeah. And this relates to the null space argument of Doherty, is that if you want to predict different things, you might choose to keep or discard different parts of the information that was in the input space, right? So the whole point about autoencoding, the first stage, is we compress it without worrying about what it is I'm trying to predict. We just try to come up with a minimal representation of the input data. And then the second step, in the second half of the neural network, we throw away the decoder part, which just checks to make sure that I've preserved all the information. And now I add the part of it which says which part of this information that's encoded in the inputs, in the latent representation of the inputs, is useful to me. And I may, if I want to predict stream flow, it might be only half of that, or it might be only a third of that, or something like that, right? If I am trying to reduce it down to a binary yes/no question, then I might have 10 bits of information stored here, but I essentially have to throw away all of it except some combination which reduces to 1 bit. Yeah. And so depending on what you're trying to predict, you might have to build a different decoding algorithm, right? I think that relates to what you were asking over there, because that determines the loss function. Now you're talking about the loss function in regard to the specific target that you're trying to match, not the use of a loss function as a generic compression device, which is a sort of a different problem. Yeah.
I guess where I struggle with understanding that is, does that require an ability to separate, and like you're saying, throw out some of the information, but is that separable? Like, can you actually separate information from,
Probably not, because
like a peak, annual peak, probably there is some information stored in the observations that are nowhere near that
Yeah.
time period, or, in the low flow, or somewhere else. So are they separable like that?
I would argue not, because your latent representation is going to store the information, but some of the information required to predict A is similar to the information required to predict B, is similar to the information required to predict C, right? So you're storing you're storing all of the information, and then you use mutual information to pick out, but you're not going to be able to say, hey, I can throw away this part or that part or that part, especially if you've got multiple things that you're trying to match. Yeah.
And I had one more question. That Jasper, when you mentioned that paper, you pulled it up, something about 4.25%, like trimming from the tails. Can you? Yeah, I would like to find that reference, because I've been struggling with something that sounds a bit similar.
There are lots of, so that's kind of a crude, I've never heard of that one before, but there are lots of robust estimators for covariance matrices. It's you know, it's a tricky problem in high dimensions, but it's a central one in multivariate
Oh,
statistics.
But this is not so much, I don't know if this is covariance.
Oh,
It's
sorry.
just that we take the samples left and right in the tails, and we just truncate the distribution. And this is what
You truncate the part of the distribution that is not reliable in your estimation.
yeah. And so when I do all this analysis without truncation, I get the same results. I don't see the effect of doing this truncation. So that's why I wanted to know whether you all are familiar with that. It must have an advantage, which I think should stabilize the results. But I
the
analysis.
problem, Jasper, is you are using samples that are reliable. Okay. So if you use the samples from a distribution that was not described by the distribution that you thought it was, right? This is your problem of misspecification, right? Then those samples would affect your result. Otherwise, truncating, you know, if I take the data from a Gaussian distribution, I throw away the tails, it's not going to make any difference, right? Because the samples are all consistent and reliable estimators of a Gaussian distribution. But if you chose a distribution that was Gaussian in the middle and some other distribution in the tails, and then you tried to estimate Gaussian statistics from it, you might have a problem.
Yeah, so I'm not sure that the data is Gaussian. It's the data is from the Lorentz operator. And so I can plot it. Actually, it's in that paper. I think it's in that paper by Van Leeuwen. He actually, in one of the last figures, he shows the distribution and then the distribution after truncation.
Tim's got his hand up.
I just had the general question whether if this is a familiar exercise that people, when they work in information theory, that they truncate individual. This is not even multivariate. They do this each individual variable by itself. They just take the histogram and then they refit a truncated Gaussian to it. Which I wasn't. I tested it here. I didn't see an effect on the results much, but it seemed to me that you do this for robustness or so. I don't know.
I'll say something, but let Tim go. Yeah.
I played a devil's advocate a little bit today, Jasper, but I think, you know, why robustness, you know, a robust R squared might be useful in practice is that, is particularly in hydrology, is that a lot of the hydrograph is essentially hallucinated. You know, we have data to support the lower hydrograph, and then we just extrapolate. Someone draws a line, and that might be one argument for why having a robust estimator could be useful instead of NSE, because NSE might be just fitting hallucinations. The other thing I want to say quickly is that another time I would love to talk more about the relationship between KGE and KL divergence.
Okay.
Thanks for bringing that up. It's something that's been nagging me.
Sure. Yeah,
Yeah,
it's a distant relationship, but conceptually you can start to think about it. Yeah.
Exactly. And the conceptual part is I think the important thing. You
Sure.
know, I've negged at it at times, but I also think some of KGE's critics kind of missed the point. But
Yeah.
that's for another time.
Well, for what it's worth, I'm working on a generalized KGE, so we can talk about that at some time. The comment I had about what you were saying earlier, Jasper, is so if you're trying to estimate central tendencies, then I can see the value of truncation, right? In some sense. But the whole point of our entropy estimation paper was to say that there's two steps in the estimation of information theoretic quantities. The first part is to estimate the PDF. And then the second part is to extract the statistics from the PDF. Yeah. And The first part is the hard problem. How do we estimate the PDF? And what we tried to say in that paper was that binning is a very non-robust way of extracting the true properties of the PDF. And if you go back to that talk and listen to it, what I tried to show was where you have large numbers of samples, you have higher confidence, and where you have small numbers of samples, you have less confidence by definition, right? And so if you've got a distribution that looks peaked and then becomes down like that, wherever you have low probabilities estimated, the bins, you have very little confidence about what the actual probability is there in that bin, okay? Now, when you try to use a median as an example, notice that your median depends on only 2 values in your data set, okay? Whereas your mean depends on an average of all the values. So you have an interesting problem with the median, which is you have to have those 2 values precisely placed, right? And then you say the median is in between these 2 values. Bye. So what we tried to do in the entropy estimation paper was we said, instead of doing that, what we're going to do is we're going to estimate every quantile. Well, not every quantile, a certain number of quantiles. Okay. So we estimate the 5%, the 10%, the 15, 20, or whatever. You have to choose something. And then to estimate those quantiles, we used bootstrapping from the data. Okay. So in essence, we used a smoothing operation, which allowed us to get a fairly robust estimate of the quantile, the position of the quantile in the PDF, which meant that you were not ignoring data points when you were trying to get the shape of the distribution. So if I had 1,000 data points and I wanted 100 quantiles, we would sample 100 data points and we would sort them in order, and we would make each of them a first estimate of the quantile. Then we'd sample another set of 100 points, and we get a second estimate of the 100 quantiles. And we do that over and over and over again. And then we take all the points that were in the first position and we would average them. Okay. And that would give us an estimate of the first quantile. And we take all the points in the second position and average them, and so on and so forth. Okay. So what we ended up doing is we ended up using all of the data points indirectly with some kind of rough weighting to give us a smoothed estimate of the shape of the probability density function, which is much more reliable than the shape of the probability density function you would get by binning. You can actually calculate theoretically the probability and the confidence in the probability. You can calculate the 95% confidence intervals on each bin probability, right? And they're very wide over here, and they're narrow over here, and then they become wide over here, right? So the question is your confidence in your confidence interval, so your confidence in your probability distribution or whatever. It's a second order uncertainty, right? And the reason I think why our method worked well, it only works, well, make some assumptions. We make some assumptions that the probability distribution is smooth and continuous, yeah? So under those conditions, it works well because it's a more robust estimator of the shape of the PDF. And once you have a more robust estimate of the shape of the PDF, then you can get a more robust estimator of entropy. And what we empirically learned was that the number of quantiles that you can estimate robustly, which gives you the correct value for entropy, was approximately 25% of the number of data points. That's empirical, okay? But if you read the paper,
Okay.
Okay. Now, what does that tell me more generally? It tells me more generally that we have to be smart about how we use the data points to estimate the shape of the PDF, right? So Manuel used a kernel-based approach, right? He investigated a kernel-based approach. Again, a kernel is doing kind of like what you're talking about in this paper. It's trying to figure out which are the points in the neighborhood which give me an accurate estimate of something that I want to estimate. And then he shows that if you want to do mutual information and you're working in higher dimensional spaces, that maybe you have to use something like a nearest neighbor kernel type of approach. Yes, Dan?
I'll take one step back. You said, okay, you sampled 100 times.
As an example, you could do it as many times as you wanted.
Yeah, so something I have struggled with is because what you're talking about is which percentiles are you evaluating the accuracy of a PDF, right?
Sure.
And I basically, yeah, just did kind of a similar experiment where I took a large sample of real catchments and but I looked at many cases where A, the number of percentiles I evaluate over, and B, sort of how much off of the ends I trim, because I don't want to include 0, I don't want to include 100. They're the most uncertain.
Yeah.
I think what you're talking about is just seeing how uncertain they are. But I just found it so sensitive to like the symmetry of how much you trim off and which percentiles you choose, because I was also very interested in the, I think it's chapter 6 or section 6 in Jasper's paper, where he does the flow duration curve evaluation. And this is what I'm working on. I have been working on it for too long now, and I'm struggling to get it across the finish line. But what I'm struggling with is that sensitivity to, well,
Sure.
we are
So-
picking a certain number of percentiles to evaluate over, and the literature is all over the map as far as what they choose.
So we didn't specify how many. We said we're going to learn it, right?
Okay.
By empirical example. And just for the examples that we worked on, but a couple of more things I wanted to say. One was we have to specify the minimum and the maximum. And so we use the smallest data point and the largest data point in the sample for that. Okay. Otherwise, you have to figure out what to do and project them and so on and so forth. So we did that. The second thing is when you do the bootstrapping approach, okay, there's going to be a slight tendency for your distribution to be slightly more peaked and slightly more squished this way, because the samples towards the end are going to have more of a bias in the estimation, okay? Because you have less samples towards the outside, so your estimate of the quantile is going to be shifted inwards slightly, right? There's going to be a slight bias, and you need a lot of samples to eliminate that bias, right? So, so there are a couple of, approximations that went into that we just had to say, use the smallest sample and the largest sample for the range. And if you know it's 0, then specify 0, right? And you know it can't be larger than this, specify that, right? Because that gives you a firm bound. But if you don't know what it is, use the data. And then these effects sort of compensate for each other, right? Picking the smallest and largest and so on have a sort of effect on the entropy, or choosing an upper and lower bound have an effect on the entropy. The fact that we're using a piecewise linear approximation, okay, means because we're estimating the CDF, okay, when you convert it to a PDF, it means it's a piecewise constant approximation. So that adds a little bit of entropy, right? So the net effect of all these seem to be that if you have n data points, you can robustly approximately estimate n by 4 quantiles. And it sort of feels intuitively okay, but I can't argue theoretically that there's a correct number or something like that, because you got all these other effects going on. Yeah.
So I think
I'm sorry, guys. Yeah, I've got
it's getting late.
another meeting. Yeah.
Yeah. So anyway, so talking about anyway, there's very things I still like to talk, but it's for another time then. About the van der Vaart, Aart van der Vaart. He's the king in non-parametric Bayesian inference, and I saw a talk he presented where the uncertainty in it's about CDF fitting, and that's where he uses a prior to turn into statistical uncertainty, the uncertainty in your assumption. So he uses a prior on CDF fitting and then shows what the effect is. Yeah, so anyway, related to what we talked about, because yes, one of the big things when you start with information theory that you're discrete and continuous, that they're not the same. That's already really difficult to comprehend. There's different units, different, so yeah.
And
To start with, but anyway.
The second thing is what I've learned over the years is never calculate a statistic without bootstrapping.
Yes, yeah. But Hoshan, I still have one last question. So the median is more robust to outliers than the mean.
Agreed.
But yes, you don't use all your samples.
If you have small samples, right, the uncertainty associated with the median can be quite large. That's all I'm saying, right?
Yeah.
You would have to repeat it many times. So even if you wanted to calculate the median, I would still bootstrap, is my point.
Yeah.
Okay. Yeah.
All
right. Sorry, guys, gotta go. Thank you. That was
Thank you.
a session.
Thank you. Then, if you have questions, let's set up a meeting otherwise, okay?
Okay, yeah,
If you have questions about the, I thought you said something about the flow duration curve.
Yeah.
Then just email me then, okay?
That
Then
would
we
be
can
great,
meet.
thank you.
Because I would not like you to be stuck on stuff. That's horrible.
Yeah, like your example is a bit different because you're talking about forecasting, and I'm looking strictly at prediction of the flow duration curve in ungauged basins. So it's not really a forecasting. So like I looked at your example, it was a really clear example and I really liked it, but I don't think it's quite applicable in my case, but I'm trying to work through an approach. So I'll formulate a concise email and I'll send it to you.
Yeah. Please do.
Thank you.
I must say between us, when you're how to say this, Hoshin is great, but at the same time, his answer is not always explicit, like do this. It's more a general thing. He can be very explicit when it's about a specific topic and all that. And I got the feeling from what you asked that you had a little bit more direct guidance. I may be wrong, but that you know essentially how to approach this problem. So I'm happy to talk to you. So write me an email and then we'll meet up. But because I'm also very interested just to see this being applied.
Okay.
It's easy to compute this and it avoids all the issues with where people say I'm only interested at these exceedance probabilities and then this is just one measure. So I'm very interested to seeing it being applied. So it's in my best interest as well to help you and hopefully that it helps the field further. Because that's what I like about the information theory, right? What your advisor has been doing for a while.
Okay. All right, thanks so much.
Oh, you're welcome. It's nice weather there, I see.
Yeah, we're hanging on to our last bit of summer here, so.
Okay.
All right.
Take care. Email me.
Bye.
Take care. Bye. Bye, Joe. Bye.